Hey everyone, I'm back with another update to the Alpha-4017 project. Over the past several months, since I posted my last one, I have gotten so much done. I've gotten the instructions set down, the full block diagram down. I have hopefully foolproofed all my race condition flaws, if there were any. And so now I am just waiting on a few more parts that I will be ordering soon, as well as just construction and testing, and then I'm ready to go. This is kind of the assembled board, or one of the assembled boards for the Alpha-4017. Of course, there's no dip sockets for these. I'm probably going to get a load of dip sockets for these sooner or later. But this is just the board 1 of 2, hopefully, not of 3. But this board is the memory and sequencing and power circuit. So what we have here is that we have all these dip switches that are going to be your programming space, and for each instruction, or actually program slot, or address, I should say. In each address, there is 4 bits. Those first 4 bits are for the actual instruction calling, and then the other 4 bits are parameters. So, let's just say you wanted to call up instruction 01 or something. You would just leave switch 1, 2, 3 off, and turn 4 on. And then if that required a parameter, say, of 2, and since binary 2 is 0, 0, 1, 0, you would have switch 6 off, switch 7 on, and then switch 8 off. So it's a 2-part programming, but I mean, it'll be tedious because you're having to flip these little toggle switches, but you won't have to switch many of them. And the reason I also called this board the memory board was, another reason why, is that it has all the registers right here. These two, actually all 6 of these chips right here are 74AC 74s, like I showed in my RAM module on my first video for this project, my RAM module using 74AC chips. And each of these is divided up into, these 2 right here are the accumulator, these 2 down here are the X register, and then these 2 are the direct output register, which these have a 4-bit output, and you can turn them into a parallel output, so to speak. Then this big old chip right here, that is a 4 to 16 multiplexer, and this is essentially what is going to decode all the instructions on the actual dip switches and call up each actual logic circuit associated with each instruction. So if you want to call up instruction 00, instruction 1 from up here, this multiplexer would just go to pin 1 or output 1 from its multiplexing, and then just send power to that, and it's more or less kind of an enabler for each instruction. Then these 2 chips up here, because the camera has such a bad focus, are 74HC401 chips, and they are, again, what I'm calling the project after. This one up here is going to be sequencing each of these memory addresses, and this one right here is going to be kind of used as a delay chip, so to speak. Actually, no, not a delay chip, sorry, it's a jump chip. It's going to be calling up, if you wanted to call, the jump instruction, jump to address, or jump a number of addresses, say 2 addresses from here, this would count every time the clock is sent out, because each address is called up in just one clock cycle. So every time you say you had this jump chip right here, it would disable the 74HC4017 up here for the sequencing each address, and enable the jump chip right here, this 4017, and it would just count the number of addresses. And then once it has reached that, it will then re-enable this, re-enable it to where it will just send power through that dip switch and to the decoder. And then, so that's pretty much how that works. And the jump switch, since I was running out of space for the instruction set, the jump instruction is going to be the closest thing that I have to a wait instruction. And then this small little chip right here, that is a NE555 timer chip, and that's just going to be the main clock generator for the entire thing. And this little area down here that I've marked off with black Sharpie, that is going to be the power circuit. So if you can imagine, just a 7805 down there with a bunch of caps and a couple of diodes or a few other things. I may have to actually get a higher current version of the 7805 because this is probably going to take a lot more than just 1 amp. I can guarantee you that. Or hopefully it won't be that much, but you never know. And then another aspect that I've designed in this thing that you have seen so far is that all these chips are in a grid pattern. And what I mean by that is that they're all lined up with column and with rows, and just down in between the chips and this row where the pencil is showing are going to be the power rails for all the chips down through here. So you can imagine just power rail going down through here between these chips and these chips, sending power to each of the chips. And all that power is going to be supplied by the power supply circuit down here. Down here we're going to have a 24-pin connector. I want to say one of those IDE connectors that you connect your hard drive with. One of those big old ribbon cable connectors. And that's going to connect this circuit right here to the other board, which is going to house the arithmetic logic unit. And that's going to be the main heart of the circuit besides all the memory and sequencing up here. And that's going to fit on this breadboard. And there's going to be a lot of space to put all the chips on there, and I hopefully will not have to stick any more chips on another board, because that will be quite a pain. And then I will have a user interface board, which is where this small circuit board comes in, and it will just have a couple of push buttons, a LED 7-segmented display here, and a 7-segmented decoder right here, and you'll just have your inputs and outputs for the entire computer. So that is pretty much all I have for now. If you have any comments, just post them. If you have any suggestions, that would be awesome, because I do not want to fry up this, because I have worked on this quite a while. So yeah, thanks again for watching, and I'll see you later.